Uh, so without any more wait, please, Arantxa, feel free to go on.
Thank you. Okay, so first, can you confirm you can see my screen now? Should be a presentation. I need you to speak because while I'm
Chat,
speaking.
chat
Okay.
says yes, so I assume
Okay,
it can
great.
be.
So the idea of this presentation is that I have some slides. Some of them are quite technical, some heavy maths, and as this is like more, I thought of it more as like a study group. You can ask as many questions as you wanted. I have a tablet if we need to stop the presentation, go to a whiteboard, do some maths, and come back. Please don't leave the questions for the end because it's quite a heavy presentation, and it's important that you are like understanding and following each step. Also, I cannot see the chat. I cannot see anything at this point. I only see my screen. So please, like, unmute yourself and interrupt. And if this is falling by any mean, please like write on Telegram something because again, I don't get the notifications for Discord chat. So let's start. In this talk, we are going to dive from actually not even Caulk by a work by Thomas et al. That is called Aggregatable Subvector Commitments. Then we'll go to Caulk, that is a joint work with other people in the foundation, like Mary, Dimitri, Vitalik, Mark, and also Anka from Protocol Labs. And then to Caulk Plus, which is a work by Posen and Katis. Everything is very like related, but I really thought it was important to start in this work by Thomas et al. I think it's one of the cores of Caulk and also a work of its own independent interest. But let's talk a bit about Caulk, which is like the Caulk between these two papers, the joint part. Caulk aims to construct lookup tables and membership proofs. We can see membership proofs as a special case of lookup tables when we are just looking at one element. And in Caulk, we want both lookup tables and membership proofs to be hidden, which means we have like a public set or a public table, and then we want to prove knowledge of elements that belong to this table without revealing which are the elements that we are opening. And these kind of problems have been solved before. You may be familiar. There are solutions in the discrete log setting. These ones I don't think you are so familiar because they are not so efficient and a bit older. In a discrete log setting, we always have a transparent setup. Well, no, we can have a transparent setup. And then in most of the cases, what we pay is that we have a linear prover and linear verifier. So linear verifier is like our prohibited thingy. Then we have RSA accumulators, which I'm confident you are more familiar with. RSA accumulators have a constant prover, like constructions based on RSA groups, have a constant prover, which is not trivial. It's something that we are very interested in. But RSA groups need trusty parameters that are not very clear how to compute them efficiently, even using multi-party computation or such. And then we have Merkle tree solutions. This was, let's say, like the state-of-the-art solution before Caulk, I would say. The thing is that when you want to prove membership using a Merkle tree, you have a transparent setup, but then to add zero knowledge, you need to put a zero knowledge narc on top. So that's quite heavy machinery. And then we have the pairing-based solutions. In pairing-based schemes, we usually can achieve a constant proof and a constant verifier quite easily. But the problem becomes with the prover. The prover is quite expensive in all pairing-based constructions. Still, Caulk will fall in this setting. We go for the pairing-based one. And what we achieve is a protocol that has a logarithmic prover. It still has a constant proof, and we sacrifice a bit the verifier, but it's in the field, and we are okay with that. So why do we construct Caulk to be a pairing-based protocol? So the first reason is efficiency, what I mentioned before. In the pairing base, it's easy to achieve constant verifier and constant side proofs. But then there is this modularity. We want Caulk to be, or we wanted Caulk to be usable into other schemes, zero-knowledge snarks, for instance. And when we construct in the pairing base setting and all the, let's say, newest protocols constructing this setting, we have this universal univariate SRS. So basically the one that it's now being computed through the KCG ceremony. And it's important that this SRS is universal because even though it's a very heavy process and very expensive process to create this SRS, once we have it, we can use it for many different applications. Now, how does Caulk work, and what is the relation between Caulk and vector commitments? Let's see how can we construct lookup tables or membership proofs starting from vector commitments. So for membership proofs, we can say, okay, what is a membership proof? We have a set of authorized users, and we want to prove ourselves part of this group. So this set of authorized users can be expressed as a vector of public keys. And this vector is public. The set of authorized users is public. And if I want to prove myself into this group, but I want to hide my identity, what we can do using vector commitments is isolate one of these public keys, but in zero knowledge. This yellow circle means this is still hidden. And then I can prove knowledge of the corresponding secret key. But it's important that this opening that I do in the vector, selecting one element and isolating it, it's done in zero knowledge. The part where I prove knowledge of the secret key, that's another algorithm. But we can see membership proofs as a vector opening problem. Same happens with range proofs, quite the other way around. If I have an element, a secret element, I want to prove it's within a range, I could see that range as a vector of integers that go from, for instance, n1 to n2. And if I can prove that my hidden element is a part of this vector, is an element in this vector, then I'm proving that this element falls within that range. In this case, again, the vector, the big one, is public, the range is public, and what I want to hide is the position or the value that I'm extracting from it. Lookup tables can be thought, for instance, as many range proofs all at the same time. So I have a vector, I have a hidden vector, and then I want to prove that all the elements in this vector actually come from some public set. Doesn't matter the order, doesn't matter how many I'm taking, I can take them with repetitions. And this is the case we are going to focus on because, as I mentioned before, membership proofs and range proofs, as I mentioned, are particular cases of this lookup table. So the recipe in Caulk. Let's first see like a high-level overview, and then we are going through everything. The main idea, remember, we want to achieve a lookup argument that is logarithmic on the size of the big table. So first step, we start with our public table, and we will extract from this public table only the elements that are in our lookup. And I will call this set here, this vector that is the hidden one, I will call it the hidden vector or a hidden set. So from the big table, we are extracting first only the elements that we are going to use. And then, of course, this will be in zero knowledge. We want to hide the positions or the values that we are extracting from the big vector. And now we are working with something that is way smaller. And this is, we will prove the link with the table that we are indeed extracting some subtable or subvector of the public and original one. And then from here, we're going to do the link with the hidden set. So instead of going directly from the public table to our lookup, we are making one step in the middle, which is a subtable. a subtable that only uses the elements that we need for the hidden set. And I hope here you get some intuition that this doesn't need to depend on big N anymore, big N being the size of the big vector. The relation between the subtable and the big table could depend on N. But the other part, linking the hidden set with the subtable, shouldn't depend on N because there is nothing that really depends on N anymore. This is the recipe that we follow in Caulk, the recipe that is followed in Caulk Plus and in Baloo as well. And it worked. So these are the numbers for our first implementation of Caulk. I don't know if you can see my cursor, but the orange line at the bottom is Caulk for membership groups, meaning that we are opening just one element. And in the x-axis, we have the size of the big table, the logarithm of the size of the big table. So we are opening in tables of size 2 to the 6, 2 to the 8, 2 to the 22, just one element. And the yellow line in the bottom is Caulk. Then we have RSA accumulators. As I said before, the prover in RSA accumulators is constant on the size of the table. So it's always the same cost. And then we have in the green line, Merkle tree with Poseidon hashes and Marlin on top. No, 116 on top, sorry. And then at the very top, we have Merkle trees with Shah hashes and Growth 16 on top. So Caulk is really an improvement over previous works. And for lookup tables, when we are opening many elements, we have these numbers. So in the x-axis, now we have the size of the table of the hidden set of the elements we are looking at. So this is not a logarithmic, this is 10 elements, 16 elements, up to 50 elements. And then the different lines are the blue line at the bottom is Caulk when the big table has size 2 to the 8. As you can see, like this is very efficient, but then when we go to tables of 2 to the 20, the orange line, it becomes closer to RSA accumulators. Once again, RSA accumulator, in this case, the work by Campanelli et al. Called Harissa, is constant, only one line, because it doesn't matter how big the table is. The prover here only depends on the amount of lookups that they are performing. And then we have Merkle tree with Poseidon hashes. Like Merkle tree with Shah hashes were way too inefficient to be in this table. And we have again Merkle trees with Poseidon hashes for tables of size 2 to the 20 and 2 to the 8. So Caulk is pretty cool. More efficient than RSA accumulators, I would say, up to tables of size 2 to the 22, 2 to the 23. But then there is Caulk Plus. Caulk Plus is a work that comes after, and it actually removes the dependency on the big table. So if Caulk is logarithmic in the big table, Caulk Plus is just constant. So this line for membership proofs is going to be constant. So if I'm opening one element in a table of any size, the prover cost will be the same. And these two lines, the ones that we have for tables of size 2 to the 20 and 2 to the 8, will be just one line. We achieve a prover that is constant on the size of the big table, which is super cool. And it gets even better, but that's probably for another lecture. So we say we need vector commitments. We are thinking of lookup tables and membership proofs as problems with vector. So let's start with some definitions. What is a vector commitment? Vector commitments were introduced by Catalano and Fiore back in 2013. And a vector commitment scheme consists of 4 algorithms, which I think you are already kind of familiar with from a more practical or implementation perspective. There is a setup. The setup takes as input the security parameters and the bound on the size of the vector, and outputs the structure reference string. Some we will see later which this can be, but if you are familiarized with that, this is basically the ceremony. What is the KCG ceremony is creating is this SRS. But this is for a special case of KCG. There is a commitment phase that takes as input the vector and this SRS and outputs a commitment to this vector. One requirement by Catalogner and Fiore when they define these vector commitments is that this commitment has to be independent of the size of the vector. So it's a shrinking commitment. It's supposed to really store all the information of V in a very succinct way. Then there is an opening procedure that will be performed by our prover. And again, as defined back in 2013, this open procedure is to open just one position. So it takes as input the vector, a position I, and outputs the value that the vector, that the element of the vector in that position takes, a proof that actually that is the value stored in that position. And then the verifier just has to take as input this commitment, this position, the value that the prover claims is in that position, the proof, and decides whether to accept or reject. And if you see, like in membership proofs, what we are doing is exactly this, just opening the vector at one position. In our case, we want this position to be hidden, but it's basically a vector commitment opening as defined back in the seminal work. And now, KCG, the famous KCG, let's see some maths on KCG. And here, please stop me if you are lost at any point. So the first thing to say is that KCG is not a vector commitment scheme, it's a polynomial commitment scheme. So consider a polynomial P and some point in our field alpha. What KCG aims to prove, it aims to be a scheme where a prover can convince a verifier that P evaluated in alpha takes value A. Yeah, so alpha is a point that the verifier knows, the prover knows. They both have access to a commitment to the polynomial. And the prover wants to convince the verifier, hey, P in alpha equals A. And the observation in KCG is that this is true if and only if x minus alpha divides px minus a. Or what is the same to say is that alpha is a root of the polynomial px minus a. How do we prove that x minus alpha divides px minus a? By providing the quotient of the division. So if there exists an h such that px minus a equals x minus alpha times h, is because x minus alpha divides px minus I, and this means that if we evaluate both sides of the equation in alpha, what we have in the right side is 0, because we get the term alpha minus alpha, and then p of alpha minus a equals 0. So this is true if and only if it is true that p in alpha gets value a. So this is the observation in KCG for polynomials. We want to use KCG as a vector commitment. What we say is we have this. We have a way to open polynomials. So can we find, given our vector v, many points such that if our vector, here there is a typo, vector v has size big N. So can I find n points in the field and create a polynomial such that when I open this polynomial in each of these points, I get the positions? So I'll recap. We have a polynomial, a way to prove the polynomials open to certain values. So p evaluated in some value gives us another value. And now we want to use that to open vectors at all their different positions. So a vector commitment scheme should give us a procedure to open any position of the vector. So what we say, okay, do I have different evaluation points such that if I get one polynomial, and evaluate it in each of these evaluation points, I get one of the positions. And I need that for all positions. So the answer is yes. So there exists such polynomial. And once we have constructed that polynomial, that we will see just in next slide, we have that when we want to open one position of the vector, it's enough to open that polynomial to one of these evaluation points. I have called these evaluation points omega because even though we are not going to use this for this presentation, these points are root of unities. But if you are not familiarized with that, or if this just like put some complexity that is unnecessary, you can think of this vector of 1 omega square stuff as alpha 1, alpha 2, alpha 3, all your favorite evaluation points. So how do we construct this vector? This polynomial that encodes the vector, that relates us back to the vector. What we are going to use are Lagrange interpolation polynomials. So if you're not familiarized with that, the Lagrange interpolation polynomials are related to a set. In this case, the set is a set of all the powers of omega from 0 to n-1. And they are defined the following way. There will be big N Lagrange polynomials, and each of them has degree n-1, and is a product of a quotient between all the x minus omega to the j, where j is not equal to I if we are defining the polynomial I. And in the quotient, what we have is omega to the I that we are defining, minus omega to the j. So what happens with these polynomials? First of all, they conform a basis of the polynomials of degree n-1. And when I take the polynomial lambda I and I evaluate it in one of the roots corresponds one of the evaluation points, the one I decided is going to be linked with position I. What we get is that the numerator equals my denominator, so I will have the same thing like in both sides of the fraction, and then this is going to be 1. But when I evaluate this polynomial in another point that is different from I, so in the point I decide is going to be in position S, then there is one element on the top of my fraction that is going to be 0. And then all my polynomial will take value 0 because it's a product. So I get one factor that is 0 and everything is gone. So the magic with the Lagrange polynomial is that we can, when we interpolate a set, we get these polynomials that get value 1 in one of these elements and 0 everywhere else. And with these polynomials is that we are going to construct the polynomial that represents the vector. How? Well, we'll say v of x is going to be the linear combination of positions I with Lagrange polynomial I. So when I take this dx and I evaluate it in omega I minus 1, I will get vi. And now I have a relation as I wanted before. I have a polynomial. I have KCG to open that polynomial to different points. But I have constructed that polynomial in such a way that when I open it to specific points, I get elements of my vector. So for a membership proof, for instance, if my vector is the vector of all public keys, and I construct the polynomial in this way, just by giving the opening in one position and proving that's my public key, I have the membership proof. So this is the maths for KCG. So as a vector commitment, KCG does the following. We have a setup. The setup takes the security parameters and the amount on the size of our vector n, and outputs the SRS. The SRS here is the I assume, sorry, here some familiarity with pairings, and I am just using the notation directly. But if anyone is not familiar with pairings, we can make a stop here. And these areas will be powers of some secret element in groups G1 and G2 from some bilinear groups with efficient pairings. And these powers, we will use all of them from 0 to n. Again, this is what is actually now being performed in the KCG ceremony. So we want a setup for the KCG vector or polynomial commitment. And then the commitment algorithm just takes a vector v, computes this polynomial v that I mentioned before, but the commitment is in the group. So it's int. It's just one element in the group. That is this polynomial evaluated in this secret point, in this case, in group G1. To open this vector to one element, or to open this polynomial to one element, the open algorithm takes the SRS, all these powers of rho, the vector and position I, and we find the quotient of this division, as I said before. So the quotient of the division of the polynomial that encodes the vector, minus the value I'm claiming it's stored in position I, over x minus omega I. Typo here, this is omega I to the minus 1. But still, the point that corresponds to position I. And then I will check this with a pen. So the commitment that is in group 1 minus the field element S that the prover is claiming it's in position I equals the quotient. We don't care about the shape of H. H is, as soon as it is a polynomial, we're okay. A group element, we're okay. And then the verifier will perform itself this rho minus omega to the I in group 2 to check this this equation in the group as a pair. If this is true, if this pairing is satisfied, if this pairing equation is satisfied, then the verifier is convinced that in position I of vector B, we have element S. So now that we have vector commitments, we can see that all these things that I mentioned before, taking the table, making a subtable, linking that with a hidden set, all of this is going to be done with vector commitments. So we won't have the table as a vector, we will have a vector commitment, a commitment to the table. We'll have a commitment to the subtable that is going to be hidden. Very important. We want not to reveal our positions or values. And then we have another hidden vector commitment.
Arantxa, sorry to interrupt. We have a question which is C is an elliptic curve point and S is a scalar. What do you mean by C minus S?
You have to put S in. So this notation with the brackets, for instance, H evaluated in rho is G1 to H to the rho, that's on the exponent. So when you want to do C minus S, what you are actually doing with S is put it in the exponent, invert it, and then multiply that by your element C, that you can do because S is in the field, and then what you will have is G1 to the vector that is inside C minus S. Does it make any sense?
For me, it makes sense. For me, it makes sense. If you want, I shared you a link on Telegram so that you can do whiteboard, and maybe it's easier for you. You can join the link that I send you with the tablet and also with your computer, and share the link of the website instead of the presentation when you want to swap, basically.
Okay. So who has this question?
Francisco, basically. If he asks to speak, I can let him, but otherwise I have no way to allow him. So Francisco, if you want to ask, it's
okay. I have the. Can you share the link to the whiteboard, Carlos? So I don't have
to everyone, so that you don't need to.
Yeah.
Yeah, sure, definitely,
Let's
definitely.
see. Let me know when you can see the whiteboard.
The link is in the chat already, so if
Okay,
anyone
I
is
have
able to
some
make it now.
visitors.
Okay, nice.
I hope Francisco is here. Well, I think we have enough people. So this is a notation I assume you were familiarized with. I am sorry for that. But when we have our pairing that goes from a bilinear group to some target group, what's this G1 group? I assume it has some generator. I mean, I don't assume. We set a generator that is called G1. Okay, I'm having some problems to write. Okay, G1 is a generator, and G2 is a generator of group 2. So when I say, for instance, we have all the powers of raw, like this, what I'm saying is that we have G1 to the raw, to raw squared, so on and so forth. And then the commitment here, I say, is the sum of all the VI's lambda I in raw. This means what we have is G1 to this polynomial evaluated in raw. And we can perform this from the SRS because we are only doing linear operations. Because raw is unknown, we just have this as a whole, as a group element. But as soon as we know which one is each power, we can just do the linear operations. And then when I say we have Z minus S, I mean we have G to the sum of the VI lambda I raw minus S. How do I do this? Sorry, this is G1. Well, I start from the commitment, which I cannot disaggregate. I cannot touch the exponent here because I have been given this as whole, as a group element. But I can do this times G1 times to minus S. So this is I can calculate G1 to the S and then invert it and multiply it by the commitment. This is what I cannot touch because I don't know what is in the exponent. But because S is a field element and I know it, I can perform this multiplication and get this side of the pairing. I would like Francisco to say if this answered his question or not.
I think he said, yeah, he said yes.
Nice. Okay, perfect. And now we have the board. That's amazing. But let's go back to the screen. And we have this for. Okay, someone else has been. Okay. And we have this just as an extra. So as I said before, now we have a way to see lookup tables as vector problems. And then we have vector commitment schemes. So we want to do this table, this link between a subtable that now we can call subvector to the previous one and the link to the hidden set, all of that in terms of vector commitments. We want to link vector commitments in some way. So first step, we have a public table, a public vector, and some secret vector And we want to prove that every element in the secret vector comes from the public one. In vector terminology, what we want is a subvector commitment. Prove that the second one is a subvector of the initial tail. So a subvector commitment scheme is almost the same as a vector commitment scheme as defined by Catalan and Fiorer. Subvector commitments are defined by Lai and Malavolta and Bonnet et al. And instead of opening one position, what we will do is open a set of positions. So I have my vector, a commitment to my vector, and instead of opening just one S, I want to open a bunch of this S and say, hey, for this set I of positions, this set S are the corresponding values. Everything will be the same in the sense that the prover will output a proof, but in this case with a set of elements, of claim values, and the verifier will check this proof, will know these SIs, and will try to see if this is indeed a subvector or not. Then accept or rejects. And the subvector commitment that we are using here is the one by Tomescu et al. This is a work that is from 2020, and it has 2 key points. The first observation they do is, okay, we want to open subvectors. We know how to open individual positions. We have this KCG sort of thing that tell us, hey, if SI is the element, the value of the position I of our vector, then, and if you have constructed V, as we say within Lagrange interpolation polynomials, then this equation on the left is satisfied. And then we have the same for every position. So let's say some position J, we have the same thing. We have an HJ that divides, that is a quotient of the division between Vx minus Sj over x minus omega j to the minus 1. And what they say is, okay, let's do this both in one shot. And here we have some more heavy maths, which is we can interpolate anything we want. Lagrange interpolation works for any set of any size you want. And the polynomials that you will create, the Lagrange polynomials, will have degree the size of your vector. So what they say in this work, they say, okay, let's interpolate just these 2 positions. So the Lagrange polynomials are just of degree 1, super simple. We have 2, tau I and tau j. So tau I corresponding to I, it will be just x minus the other interpolation point over the interpolation point corresponding to position I minus the other interpolation point. And this is a polynomial of degree 1 that will take value 1 in the ith interpolation point and value 0 in the other one. Everything else, in all the other interpolation points, it will take whatever value. It just interpolates this set of 2 elements. And with these Lagrange polynomials, we will create one new polynomial that is the polynomial as with the same idea that we create this Vx for this huge vector, we are creating this small polynomial of degree 1 for these 2 points, for this subvector of only 2 points. So this is going to be Si times tau I plus Sj times tau j. And what we want to prove now is that Vx minus this new polynomial vanishes in both positions. Before we have Vx minus Si vanishes at omega I minus 1. Well, now we have Vx minus this other polynomial vanishes in both positions, in I and in j. This is indeed true. For instance, if we evaluate this in the interpolation point I, V evaluated in this point will take value Vi, because this is the same interpolation point we construct the Lagranges with. Then the taus, one will take value 1 and the other one will take value 0. That's how we constructed them. And then in the right side, there is one of the factors oops, sorry, one takes value 1, the other takes value 0, so we just keep the one that is multiplied by 1. And then in the right side of the equation, there is one of the factors that will take value 0, which is actually the other factor, not the one I highlighted, but anyways. And then this is true if and only if indeed in position I, the vector has element Si. So what is the first key point here? It's that instead to prove two different openings, two different positions, instead of proving them separately, I can do it all at one shot. And two other things that are very important. The first one is that this new polynomial that I'm creating, it has very small degree. So if I have to manipulate the big polynomial, the polynomial that corresponds to vector v, I am working with degree big N, and everything I do to that polynomial will take me time n. But if I manage to create polynomials with smaller degree, now I can do whatever I want, because everything will be, for instance, here linear in the size of this smaller polynomial, which is 1. So this is the first thing that is super cool. You can prove subvectors with very small polynomials. And the other thing, and this is probably something that if you are not familiar with will ring a bell, is the fact that we can pre-compute the proofs. So as I said before, in the pairing-based setting, we have a cool constant prover, constant verifier, but the prover, constant proof, constant verifier, but the prover is always the one paying the price. So if we can pre-compute some part of the proof, we can save the prover some work. That's the path we should take in order to achieve a prover that does not depend, or that only depends logarithmically on the size of the big vector. So what does it mean to pre-compute these proofs? For instance, in this case, again, where we have just two openings, there is an hi that proves Si belongs to vector v in position I, and hj that proves the same for position j and sj. And then there is this h that proves all of them at one shot, both of them at one shot. At the first glance, we don't care about this h, what this h is. It's just proving divisibility. So to prove divisibility, I have to prove there is a quotient and no rest. And this is everything h is doing here. But it turns out that actually this h is a linear combination of the previous ones. So if I'm opening two elements, the h I have to calculate is a linear combination of the h of each individual proofs. And this combination is with constants that do not depend on v at all. They only depend on the interpolation points. So these constants are, this h is easy to compute if we have pre-computed hi and hj. So what's actually is going to happen is that the prover will pre-compute this and store it as group elements. So at one shot, the prover will pre-compute all these his. This, thanks to the procedure by Face and Kovacevic, or Dankrad and Dimitri. This can be done in time n log n. So these are all polynomials of size n, and we have n of them. So trivially, this should take n squared time. But thanks to this procedure, we can do it in time n log n. And then the prover stores it in their memory. It will take space n, but that's just once for the vector. So for instance, if you think on membership proofs, these things can be pre-computed and be public. The set of openings, the set of public keys is public. The pre-computed proofs can also be public, and then we do some strategy to hide them. But that can be public. The same for range proofs. We can just pre-compute all the openings of different positions. And for lookup tables, as soon as we are kind of reusing this table, this makes sense. If I'm going to do just one shot on this table, then it doesn't pay off. It's a lot of memory and a lot of work. But if it is something that we are doing over and over, we're working with the same table many times, it does make sense to have these elements pre-computed. And then the prover has access to all these group elements when it wants to open one set I. And here we will generalize not only to a set of 2 elements, but more. The prover will first calculate these Lagrange interpolation polynomials that interpolate the points that we are opening, nothing else. And these polynomials will have degree the size of our subset. Then it will calculate the polynomial corresponding to this new subvector with those taus and send it in the group. And then it will calculate H as a linear combination of the pre-computed values. So this takes time, size of I. So it's I exponentiations in the group. The verifier checks this in the as a pairing, so that B minus BI, which is the vector of the claim opening values, the claim subvector, is actually something times, and as before we have x minus omega I, x minus omega j, well, we have all the x minus omega, the corresponding positions in the group. So this is tau, because now we are in the pairings, we use tau to evaluate the polynomial, and this is what the verifier will check. As a first, trivially, this will take the verifier time I in the group to calculate this polynomial, because it's a polynomial of degree I. But in Caulk, we do something different. So let's recap. We had a table, and we had a subtable.
Sorry, Arantxa, I have
Yes.
one question. You said that basically the protocol only pays off if you actually reuse the same table over and over. But I was wondering if you reuse most of the same table, but not exactly the same, in the sense of you actually update small entries on the table. Like, let's say I have a set of 10 people, I remove one or I add one more. Does it pay off if I do some kind of approach like this?
Well, this is a problem in Caulk, actually, because these proofs, these HIs, depend on every value. So this H is a polynomial that includes all the positions P. So if you change one value in your table, you have to change all the proofs. So updating each proof, it's cheap, it's constant time. It's just changing the position. If I have modified B5, I just have to change B5, but I have to do it in all proofs, and that takes time n. So it's not very updates friendly Caulk.
Okay. Thank you.
So
I think Todd has also a question.
Yeah, could I please ask, how does the verifier get the orange term in the pairing, that product?
That's something that the verifier can compute itself. Now I'm presenting the work by Tomescu et al., where the prover doesn't aim to hide these positions. So as a subvector opening, the verifier knows the set I and can compute this itself, because the interpolation points are public, and set I so far is also public in the subvector opening, not in our case.
Okay, thank you.
So this is a polynomial of degree I, size of I, that the verifier can compute itself.
So what does this convince the verifier is true, that V sub I commitment really is a commitment to the polynomial as you've described it on the left?
So how can I say this without talking about assumption?
It's okay if it's...
No, it's okay, but this VI can only hide group elements. I mean, it's a group element, sorry. So whatever BI is she to something. She wants to something in this case. This something, because this equation is satisfied, is something that takes the right values when evaluated at the interpolation point. So it cannot be a constant. BI cannot hide just an element, because every time I'm evaluating my polynomial in different interpolation points, it's taking a different value. So here what we are using actually is the algebraic group model that says that whatever the prover sends you in a group can only be a polynomial evaluated in the SRS. So if it is anything that the prover put there, if it is a random element, then it's a polynomial of degree 0. But if this BI has some structure, if this element in the commitment BI is doing something more, the only thing it can do is be a polynomial evaluated in the SRS. And I mean, I can send you some more explicit thingy or some reference on how this works. But the idea is that the only things that you can put in the group are random elements or polynomials evaluated in raw. Are you doing a polynomial evaluated in another element? That counts as a random element, as a constant term. If it has a meaning in this pairing, then it's a polynomial evaluated in raw.
Thank you.
Hope that give us some.
That's helpful. Yes, thank
some
you.
intuition too. Like there is nothing, but if you cannot access these taus because of the discrete log, then you cannot do anything with them. You can just put constant terms of polynomials evaluated in tau, meaning that you have just performed linear operations to this group element. Now, going back to Caulk, we have a vector, we have a subvector that is hidden, and we want to prove that this subvector, we have them both committed using different Lagrange bases. So the first one has degree n, big N, -1, and the second one has just degree size of I -1. In this case, size of I will be 5. It's the amount of elements in our subtype. Now, to prove this is well formed, we have to link them. And we said that to link them, we use Thomas et al. But now, well, this is in the field, but the pairing is this one. As you asked before, what happens with this polynomial? In the subvector setting, this polynomial is actually calculated by the verifier because the verifier knows I. But now we want to hide it. We want some zero knowledge here. So the prover won't communicate to the verifier I, but will just send some element. It's an element in the second group, in group G2. And now, how do we convince our verifier that this equation implies that BI encodes as a vector of B? This is the dependency on N, or Caulk. So in Caulk, this takes time size of B of I times log size of the big table. And the way we do that is we just prove that Z is some polynomial that vanishes at some interpolation points. And some of the previous ones. So we have n interpolation points that we use to construct the big vector. And it is enough to prove that whatever is here interpolates a subset of that. But then, so as I said before, this takes time and log n, but then there is Caulk plus. Caulk plus proves the same thing with a very similar idea, but in time that does not depend on the size of big N. So let's go with more detail about how do we prove this in zero knowledge. How do we get rid of the part of the verifier knowing the subset that we are opening? So recap. We have polynomial B that encodes the big vector, we have polynomial bi that encodes the subvector. We have this polynomial that should vanish at all the interpolation points of I. And then we have the quotient that we just care about its existence, but nothing else. And now, to prove that this is well-formed, we first see that there is a polynomial that vanishes all the interpolation points. And that is public. Because all the interpolation points are public, what we don't want to reveal is which ones we are using. So the big polynomial of size big N, that one is public. And to prove that this polynomial vanishes at some point, either in the field or in the group, what we have to prove is that it divides the big one. So we have the big one that is a product of monomials, of like irreducible polynomials. So if there is one that has just some of those terms, it must divide it. And the way, I mean, this is the approach of Caulk class. In Caulk, we have a very complicated protocol that takes like 3 pages, 4 pages. How do we prove that some vector vanishes, some polynomial vanishes in some subset of these roots? But in Caulk class, they do it way smarter, and they say, okay, let's just prove this divisibility. We just need to prove there is a Q when multiplied by our secret element Z gives us the public vanishing polynomial, the big one. The problem with this Q is that it will have a degree n minus I, n minus size of I, and for our prover to compute this Q, that will be very expensive. But what they say is, hey, let's use the same approach as in Tomescu et al. Let's pre-compute all the individual proofs that each monomial divides the vanishing, and then do the same. Whenever I have to make a proof that some set I, set X divides the big one, I just take the linear combination of the individual proofs. And this works. And for the prover to do this, it just pre-compute another n proofs. So the prover has pre-compute n things, can pre-compute 2n things, and store them. Doesn't make a big difference in the memory. But then when it wants to prove that this subtable is well-formed, it just takes them time that is linear on the size of I, instead of computing Q from scratch, which will take time almost n. So this is the idea in Caulk Plus, and this is how they get rid of the dependency on n. So now nothing depends on n. Everything depends on the size of I. So we have proven that this subtable is well formed in a procedure that does not depend on the size of the big table at all. What does depend on the size of the big table? The precomputation step and the memory of the prover. But then, when having the interaction with the verifier, the prover does not perform any computation that depends on n, and that's huge. Once we have proven well formation, we are done with the big table. We can forget it and let it go forever. And now there is the second step. We have to link the subvector with the hidden sub. And now this won't depend on big N because we have forgotten about it. And
sorry, can I interrupt with one more question?
Yes, of course.
Thank you. On the previous slide, sorry, one more back. When you gave the QIs, maybe one more. Yeah, right here. The coefficients Ki that we use to combine them, how hard is it to compute those?
No, it's not hard. First of all, I have to say a disclaimer. These are not the same coefficients as before. Just that this was done with Google Slides. I didn't know how to do a hat or something, okay? These are coefficients that only depends, again, on the interpolation point. Constants.
I guess they must depend on the set capital I, right? That's what they're
Yeah.
confused?
They will depend on that set, but only on the interpolation points, nothing related to V or anything like that. So these are coefficients that are computed in the field and are like super easy to compute.
Okay, thank you.
So now we have to link our new vector, which is a subvector of the previous one, with a hidden set. The hidden set will have the same vector commitment idea. It's a vector that will commit to it using another basis. Why? Because this set may be even bigger than the subtable because we are doing a lot of repetitions, but also because the basis of our hidden set of the subtable, those are secret. Why? Because they're linked to the set I, which we want to keep secret. So the peripheral cannot learn this stuff. But P, the hidden set, is the thing that we are going to go and use in another protocol. For instance, if I am in a snark and I want to prove that some set of elements belongs to a range, I will have that set of elements in phi. I need to know this basis to do something useful later. And then if I'm going to open just one element and then I want to link it to my secret key, I need to know what is the commitment, how I am committing to this element. So that's why we are using different bases. So at the end, in Caulk, we use 3 different Lagrange bases. The huge one, the one that comes to the big vector, the one for the subtable, which is secret, is like an intermediate step, nothing else, and then the one related to the hidden set. And so we do this link. I'm not going to explain it by default. If you want, I can. The thing is that in Caulk, this takes time that is quadratic on the size of the hidden set. And in Caulk Plus as well. So from Caulk to Caulk Plus, there is just this saving on the dependency of on n, on big N. But then this step is the same. And then this is still n squared. And we have follow-up work. So when we started with Caulk, we say, okay, we achieved. I mean, after Halo 2 or Plockup that were linear on the size of the big table, we say, hey, we got logarithmic. It's n squared where n is the size of the hidden set, but it's logarithmic on the size of the big table. So we thought that was cool. But then they were saying, okay, no, this is not cool. This is dependent on the size of the big table. So Caulk Plus comes and says, hey, look, we don't have dependency on n. We don't have dependency on the size of the big table. It's still n squared, where n is the size of the small set, but that's okay. But then Plockup and Baloo, which are works that we have basically done together, we say, no, n squared is not good. We are going to n. So we have a prover that is only linear on the size of the small set in the group. And then there comes CQ that say, okay, but you have in the field a prover that is n log square n. That's not good. So in Caulk, we don't even mention what is a field. The field work for the prover because we were very focused on making it cheap in the group. But now that we are cheap in the group, can we make it cheaper in the field? So then CQ says, hey, yes, we can make it cheaper. We can make it n log n. And actually, then there come, like in Hypernova, I put it with a question marks because it's a different setting. It's multivariate, cannot use KCG ceremony and stuff. But they say, hey, this is not good. In the field, this is still bad. We want linear in the field. So all of this happened. So Caulk was published exactly a year ago, and all of this has happened in the last year. Hopefully, we will have other sessions where we can talk more about Plockup, Baloo. CQ is cool because it's very different. It's the first one that doesn't do this intermediate step of going through a subtable. And to be honest, this protocol to link the subtable with the hidden set in Caulk that is n squared is quite complicated. But it's the same idea of before, of like playing with the different bases and different interpolation sets and such. I can explain it to you if you want, of course. But I mean, it's obsolete already. So I don't know, up to you if you want to see that. But I think here we have covered the key points and the core observations and the core elements of all this work. So thank you very much.
Thank you so much, Arantxa. Thank you very much for everything. Is there anyone that has any questions that wants to do them now? Any particular thing you want to ask? I'm waiting for the chat because
Now I can see the chat.
okay, nice.
I can see that some people are right. Okay, it's a presentation. The presentation has been recorded.
Yeah, recorded, streamed, and will probably be uploaded on YouTube in some minutes. So, yeah.
Okay, perfect. So if you are a bit shy and don't want to ask now, like you can email me or write me on Discord or Telegram, and yeah, I will be glad to help. The thing I think it's important to say, especially for you that you work on like the real world and implementations, is that I mean what I said at the end. There are parts of Caulk that are more like obsolete already, even though I consider them like nice tricks or like nice tools to have for designing of other protocols. At this point, like the way we prove the link of the hidden set or how we prove that the subtable is well formed. I mean, if you are curious and you want to see in the paper and then ask questions, you are more than welcome. But I think it would be cool to focus more like on CQ and Baloo now, and well, of course, Hypernova.
Hopefully, we will get some sessions on those two. Hypernova is going to be a session on the 31st of May. For Baloo and CQ, let's hope there are volunteers.
No, I can do it for sure. I just need some weeks.
Thank you very much. I highly appreciate it, Arantxa. Well, it's been really nice. Thank you for being here and for sharing all of this knowledge with all of us. And yeah, hope to see you soon again here presenting.
Okay, goodbye, guys.
Take care.
Have a nice day.
Bye. Thank you, everyone.